Hello friends, in this video I'm going to take this topic ETC, electron transport chain, which is very important from PG entrance point of view. So let's get started. For explaining ETC, I will be using two routine life examples. When we have to create energy, it's like making ATP in ETC from NADH, right? So here we are making energy, but energy can neither be created nor be destroyed. It can just be converted from one form to another. So let's see how one form of energy is getting converted to another form of energy, right? Take the example of a dam, a water dam. In a water dam, flow of water from height gets converted to electricity, right? Okay, this example I'll be using. On the other hand, one more example I'll be using, that is a rolling gate. Have you seen a rolling gate at the entry of a park or a restaurant? This rolling gate has sections. If somebody has to cross the rolling gate, then we have to push the rolling gate and then we are able to enter, right? So if rolling gate is connected to something, let's say many persons are coming via some rolling gate. So rolling gate is moving, mechanical energy created. This mechanical energy is, if rolling gate is connected to something like say electrical bulb, with a converter in between which can convert this mechanical energy of rolling gate into electrical energy of the bulb, then we can light that bulb without using the normal electricity. So if rolling gate is connected to something, then the energy of rolling gate can be used, because when someone will cross the rolling gate, that will start moving, mechanical energy is created. This energy can be used, right? So these two routine life examples I'll be using to explain ETC. So let's get started. See the diagram here. In this diagram, mitochondria is shown. So let's label the diagram. This is outer mitochondrial membrane. These two inner thin lines, that is inner mitochondrial membrane, and this space is known as intermembrane space. Between the two membranes, it is intermembrane space, but the central space here, this is called mitochondrial matrix, right? So outer thick line here is outer mitochondrial membrane and two inner thin lines are inner mitochondrial membrane. The space in between is intermembrane space and the central space is mitochondrial matrix. Now let's start ETC, and ETC starts from NADH. So starting from NADH gets converted to NAD, NADH to NAD, removal of hydrogen. So this is oxidation, that is NADH gets oxidized. When NADH gets oxidized, there is removal of hydrogen or electron. If you remember, I have told you hydrogen or electron is one and the same thing, right? There is removal of electron. Now this electron is given to complex 1, then coenzyme Q, then complex 3, then cytochrome C, then complex 4, and finally to oxygen. So in this line, electron flow is occurring, and very easy to learn this list. Starting is NADH, last is oxygen, then we have 3 complexes in between, complex 1, 3 and 4. 1, 3, 4, 2 is not there. And then in between the complexes, we have 2 molecules. First is coenzyme Q and then is cytochrome C. So the sequence is NADH, then the first complex, complex 1, then coenzyme Q, then the next complex, complex 3, then next molecule cytochrome C, then next complex, complex 4, the last one, and then is oxygen, right? So in this sequence, electron flow is occurring. Now, like flow of water is a form of energy, in a dam, flow of water is a form of energy. Similarly, here, electron flow is a form of energy. We can use this energy, right? So here, we are not going to use electron here. We are going to use energy of flow of electron. Energy of flow of electron is used to do some work. And this energy of flow of electrons can only be used by complexes. Complex 1, 3 and 4, they'll be using this energy to do some work, and that work is throwing protons out. From where to where? From matrix to intermembrane space, right? Let's see how many protons are thrown out. Complex 1 is throwing 4 protons out. Complex 3 is bringing 4 protons out. Complex 4 is bringing 2 protons out. So total is 4, 4, 2. Total is 10 protons coming from one NADH, right? Now, I repeat, using the energy of electron flow, protons are coming out from the matrix into the intermembrane space. So now we are concerned with protons here. protons are chemicals which are present everywhere in the body. When ETC was not occurring in this mitochondria, then equal number of protons were present in matrix also and in intermembrane space also. They were in equilibrium, there was no disturbance. But now when ETC starts, some protons are thrown out into the intermembrane space, then these extra protons lying in the intermembrane space will create osmotic effect, right? That's why ETC is known as chemi-osmotic theory. See the name? Chemi-osmotic means chemical creating osmotic effect, right? Now, because of this osmotic effect of extra protons in the intermembrane space, they have high tendency to go back inside. And when these protons have to go back inside, see here, then they have to cross which membrane? They have to cross inner mitochondrial membrane, but they are impermeable to inner mitochondrial membrane. They can't go like this. So, there is one special gate via which they can go. There is one special gate, and this is complex 5. Complex 5 has two portions. It has F0. See F0, F0, F0 written. Means it is a rolling gate. This F0 is a proton ion channel present in inner mitochondrial membrane via which protons can go, but it is a kind of rolling gate. It is not a simple gate. It is a rolling gate, right? Now, this F0 is attached to F1. This F1 is protruding towards the mitochondrial matrix. This F1 is having enzymatic activity of ATP synthase. It has ATP synthase enzymatic activity. If this F1 subunit gets energy, then it can convert ADP to ATP, right? So let's see now. So these protons, when they have to go back inside, they can only and only go back through this complex 5 rolling gate. And when rolling gate is crossed, then mechanical energy created at rolling gate, this mechanical energy is transferred to F1 subunit, which will convert ADP to ATP. So this way, various forms of energies are getting converted from one to another, right? So I'm going to revise this. Starting from NADH, in this sequence, electron flow is occurring. When electron flow occurs, then the energy of flow of electrons is used by complexes to do some work, and that work is throwing protons out from matrix to intermembrane space. In intermembrane space, they have high osmotic effect, and because of this osmotic effect, they have high tendency to go back inside. These protons can only go back via complex 5 rolling gate, and this rolling gate F0 subunit is attached to F1 subunit. F1 can create ATP. It can convert ADP to ATP by using this energy which is coming from the mechanical energy of rolling gate, right? Now we have to see the names of these complexes. It is very easy to tell the name because you know the sequence of electron flow. This sequence of electron flow occurring from NADH via complexes finally till oxygen. So what is happening here? See, complex 1 will take electron from NADH and will give electron to coenzyme Q. So when something is losing electrons, it is getting oxidized. So the previous thing is getting oxidized, and when something is gaining electron, that is getting reduced. So when complex 1 is working, then the previous thing oxidized, next thing reduced. So name will be NADH coenzyme Q reductase. See, it is name of complex 1 is NADH coenzyme Q reductase. Now next is complex 3. For complex 3, this is previous, this is next. So name will be coenzyme Q cytochrome C reductase. See, complex 3 cytochrome C reductase, or simply cytochrome C reductase, or we can say coenzyme Q cytochrome C reductase. Then the next one, for complex 4, it is giving, cytochrome C is giving electron and oxygen is taking. You leave oxygen, just see the previous thing is getting oxidized, you know. So complex 4 name will be cytochrome C oxidase. Complex 4 name is cytochrome C oxidase. Prosthetic group is copper here. Prosthetic group means, when we say prosthetic group means it cannot be separated. Means copper can never be separated from this enzyme cytochrome C oxidase. If we say some metal is a cofactor, that means that metal can be separated also and joined also with the enzyme. But when we say prosthetic group, it is never separated because it is bound with covalent bond, right? Now I'm going to write the components of ETC. Components of ETC, all the components are lying in inner mitochondrial membrane, and these components are divided into, I will say there are 5 protein complexes. There are 5 protein complexes That is Roman number 1 to 5 we write complex 1, 2, 3, 4, 5, right? These 5 protein complexes, they are fixed within the membrane. They are fixed in the membrane. But other two things are, there are two mobile electron carriers. There are two mobile electron carriers. That means these carriers can move within the membrane, right? They can move within the membrane. And the two things are coenzyme Q, also known as ubiquinone, and another one is cytochrome C. Let me tell you, cytochrome C is a peripheral membrane protein. It is a peripheral membrane protein. Now, coenzyme Q is the only non-protein member of ETC. It is only non-protein member of ETC because cytochrome C is also a protein. These 5 complexes are also proteins. So coenzyme Q is only non-protein member of ETC. Now I was telling you that in this direction from NADH to oxygen, by all these complexes, electron flow is occurring. But why this electron flow will occur? Understand the concept. The way these six, seven things are arranged in a line, in the line, every next molecule has more tendency to gain electron, right? And this property is known as redox potential. Every next thing has more tendency to gain electron, redox potential. So can I say NADH? We are starting from NADH. So NADH has least redox potential and this oxygen has highest redox potential here. Highest redox potential. So we see here that when one NADH enters ETC, then 3 complexes are involved: complex 1, complex 3 and complex 4. Complex 1 is giving 4 protons, complex 3 also 4 protons, complex 4 is giving 2 protons. So here 10 protons are total. Total 10 protons are giving how many ATPs? That is, one NADH will give how many ATPs? You know, one NADH gives 2.5 ATPs. So I can say that 10 protons give 2.5 ATPs. 10 protons give 2.5 ATP. So tell me, complex 1 will give how many ATP? Complex 1 will give how many ATP? That is, 4 protons give how many? See, if 10 protons are giving 2.5, that means 4 protons are giving 1 ATP. So complex 1 is responsible for giving 1 ATP. Complex 3 is also giving 1 ATP. But complex 4 is giving 0.5 ATP. So total is 2.5. This way, if they ask you, be careful what they're asking. If they're asking about NADH, NADH is 2.5 ATP. But if they ask about complexes, then be careful which question they're asking. Accordingly, you have to answer. Now, we have done when ETC is starting from NADH. But you also know that ETC can start from FADH2 also, giving 1.5 ATPs. So let's see how that route will occur. When ETC starts from FADH2, then electrons are given to succinate dehydrogenase. Succinate dehydrogenase is an enzyme. I told you it is involved in TCA cycle also and it is involved in ETC also, right? Now, after succinate dehydrogenase, the electrons are given to complex 2, and that is, this complex 2 was not involved when NADH was entering ETC. So now this complex 2 will further give electrons to coenzyme Q. After that, everything is same like we did for NADH route. So here after coenzyme Q, everything is same. That is, here complex 3 will be involved, then complex 4 will be involved, like that. Okay, now let's see what is the name of complex 2. Complex 2 is taking electrons from succinate and giving to coenzyme Q. So the name will be succinate coenzyme Q reductase, right? And this complex will not throw any protons out. Like I told you, all the other 3 complexes, complex 1, 3 and 4 are giving protons out. But this complex 2 will not give any protons. As it will not give any protons, so it will not form any ATP, because you know that ATP formation depends on how many protons are thrown out, right? When 0 protons, then 0 ATP. So in this route of FADH2, complex 2, complex 3 and complex 4 are involved. Complex 2 gives 0 ATP. Complex 3, you know, it gives 1 ATP. Complex 4 gives 0.5 ATP. So this total is 1.5 ATP. You know that FADH2 gives 1.5 ATP. Now, next thing I'm going to tell is couple or coupling. means always together, like husband, wife, couple. So they are always together. But in ETC, we have to see which two things are together. In ETC, whenever electron flow occurs, then ATP formation after that will follow it. They are always together. Now, electron flow is known as oxidation because, every time the previous thing is getting oxidized, and ATP formation is known as phosphorylation. These two things, oxidation and phosphorylation, they are like a couple in ETC. So therefore, ETC is known as oxidative phosphorylation, right? So you have understood what is coupling. So now tell me, what is the meaning of uncoupling? Uncoupling means now they are not together. Like in case of a couple, husband, wife, it will be a divorce, right? Now they are no more together. And in uncoupling in ETC means one thing is there, oxidation is occurring, but phosphorylation is not occurring, right? Now let's see the examples of uncouplers. Uncouplers are substances which will create a hole in the inner mitochondrial membrane. Now let's see the example. Drug acting as uncoupler is dinitrophenol, but on the other hand, we also have natural or physiological uncoupler, in which first example I have taken is thermogenin. Thermogenin is a protein which is present in brown fat. It is a kind of proton-ion channel which is present in the inner mitochondrial membrane. Now this thermogenin is responsible for non-shivering thermogenesis. That is, it will help in the generation of heat in the body. Thermogenesis, generation of heat, but this kind of heat generation does not require shivering. It is non-shivering thermogenesis. The other one is thyroxine. Thyroxine is also an uncoupler. Now let's see understand the concept of uncoupling on the diagram of ETC. Now see the diagram, and let's say there is some uncoupler in this mitochondria. Now the diagram which is shown here, let's say there is an uncoupler in this ETC. So uncoupler example I have told you, thermogenin is uncoupler, dinitrophenol is uncoupler. You can see one uncoupler is a kind of hole in the inner mitochondrial membrane via which protons can go back inside from intermembrane space into the mitochondrial matrix, right? See, and thermogenin is also a proton-ion channel via which protons can go. I told you the normal situation was, in a normal situation in a mitochondria, what is happening is that there is only complex 5 via which protons can go back inside, right? But now let's say there is some mitochondria, let's say brown fat it is there, or it is some drug coming in some patient like dinitrophenol. So here now uncoupler is there. Uncoupler is a substance which is creating hole in the inner mitochondrial membrane. So what will happen? Let's say if NADH enters in this mitochondria, then electron flow will occur. There is no problem in electron flow. So I will say oxidation is occurring. There is no problem. But protons will be coming out, and these protons have two options how to go back. The normal gate is also present, that is complex 5 is also present. This gate, uncoupler gate, which is a simple gate, that is also present. So complex 5 is a rolling gate, it is a complex gate, right? Like if you have two options, rolling gate or a simple gate, obviously we will follow the simple gate, right? So similarly, protons now will stop using this complex rolling gate and they will simply leak through this simple gate and they will reach back inside. And this kind of gate is not having any machinery for ATP formation, so ATP formation will not occur. But what will happen that when they are going with the speed, these protons are going with the speed, with the rush they are going. Because of this speed, little bit friction will occur and little bit heat will be produced. At one channel, very negligible amount of heat is produced, right? But if the number of these channels are so many, say thousands and lakhs, then the amount of heat generated will be significant enough to maintain body's temperature, and that effect occurs in this thermogenin. Thermogenin is a protein present in brown fat. Brown fat is a tissue which is having lots of mitochondria. In each mitochondria, there are lots of thermogenin protein. These channels are there. So now the amount of heat generated will be significant enough to maintain body's temperature, and this effect is known as non-shivering thermogenesis, right? Also, thyroxine is an uncoupler. you must have read that thyroid hormones help in regulating body's temperature, right? So why? Because thyroxine is an uncoupler, right? And also you know that thyrotoxicosis patients cannot tolerate heat because too much of thyroxine in them will already make so much heat in the body that they cannot tolerate heat, right? Now there's one more drug, that is oligomycin, which is inhibitor of complex 5, but it is not an uncoupler. See the detail, what this drug is doing. Oligomycin will ligate F0 channel, the only channel which is naturally present in some mitochondria. That only channel is closed, let's say, because of oligomycin, right? So what will happen now in this mitochondria, when NADH comes for ETC, then electron flow will initially occur, but what will happen? Protons are coming out. These protons have no option how to go back. The only channel which was present, that is now closed. So these protons will stay in the intermembrane space. Now next NADH comes, 10 more protons come out. Next NADH comes, 10 more protons come out. So after some time what will happen, that all the protons of matrix are lying in the intermembrane space, that further now even oxidation cannot occur. So can I say oligomycin inhibits both oxidation and phosphorylation? So it is not an uncoupler. Uncoupling means one thing is there and other is not there. But oligomycin is inhibiting both, right? Now ADP, ATP also cannot cross in a mitochondrial membrane. So there should be a transporter for taking ADP and ATP across the inner mitochondrial membrane. And that is ADP, ATP translocase, which is present in inner mitochondrial membrane. Let's say this is inner mitochondrial membrane. Here ADP, ATP translocase is present. Translocase has two surfaces. Let's say this is the structure. There is one bigger surface on this side, smaller surface on this side. Then this translocase protein can bind one molecule. This translocase protein can bind, let's say a large molecule can be bound here, a smaller molecule can be bound here, and then this protein, see here, then this protein can flip-flop. So what will happen? This protein will come to this side, this thing will come to this side. So this way it can transfer substances across the inner mitochondrial membrane because of flip-flop mechanism, and this translocase will bring ADP inside because that is the substrate for complex 5, and it will take ATP outside. Whatever ATP is formed via ETC in the mitochondria, that will be taken outside in cytoplasm for used in anabolic reactions, right? Now there is one drug, atractyloside drug, which is the inhibitor of this ADP ATP translocase. So now see here, two questions can be asked. ADP to ATP conversion is inhibited by which drug? ADP to ATP transfer is inhibited by which thing? If conversion written, then oligomycin. If transfer written, then atractyloside. Because oligomycin is inhibiting complex 5, which is converting ADP to ATP. But atractyloside is inhibiting translocase, which is transferring ADP and ATP. So be careful which thing is asked, right? Now the next thing we have to do is inhibitors of complex 1 to 4. Inhibitor of complex 5 I have told you is oligomycin. We have done the uncouplers. Now the remaining thing left is inhibitors of complex 1 to 4. Complex 1 inhibitor is rotenone, phenobarbital. I will take a mnemonic, and the best mnemonic is in the name. See 1 written in the end of both these compounds, rotenone, phenobarbital. So they are inhibitors of complex 1, very easy to learn. Then inhibitor of complex 2, this were already done in TCA cycle, that malonate, 3-carbon compound, is the inhibitor of 3 pathways in body, beta oxidation, TCA and ETC, right? So it inhibits complex 2 of ETC. Then complex 3 inhibitor is fenformin, and complex 4 inhibitors are carbon monoxide, hydrogen sulfide, and what is this fenformin? Fenformin is like metformin, oral hypoglycemic agent. When this was used in market for diabetic patients, then it was removed from market because it was causing lactic acidosis in patients. Now let's understand why it was causing lactic acidosis. Fenformin inhibit ETC. When ETC is inhibited, then the starting material of ETC, NADH, will accumulate. When NADH accumulate, then this reaction of pyruvate to lactate conversion starts occurring, because this reaction is done by enzyme lactate dehydrogenase, which will convert NADH to NAD. So this reaction will try to use up the excess NADH present in the cells. So whenever NADH increase, then this lactic acidosis will occur. And when lactic acidosis will occur, then hyperuricemia always occurs, because lactic acid competes with uric acid for excretion by kidneys. If we have lots of lactic acid, then kidneys will keep throwing lactic acid out of the body, leaving uric acid in the body, leading to hyperuricemia, right? And let me tell you, this is also the biochemistry behind excess alcohol intake. When excess alcohol intake is done, then NADH increase will occur, and this will lead to lactic acidosis. This will lead to hyperuricemia. Therefore, we should contraindicate alcohol intake in our patients of gout and hyperuricemia, right?